Hi everyone. So in the videos this week we're going to look at the theory of general relativity. This is the theory of gravity that Einstein worked on after finishing the theory of special relativity. And in this first video I'm just going to say why a new theory of gravity is necessary. So just as we saw that Newtonian momentum had to be modified to make it consistent with special relativity, it's also true that Newtonian gravity has to be modified to make it consistent. And in this case, the modification is much more large, a big change in the conception of gravity you need in order to make it consistent with the theory of special relativity. So in this first video, I'm just going to explain what's wrong with Newton's law of gravity. Why is it not consistent with special relativity? Okay. So we'll start just by defining what Newton's law of gravity says. So imagine we have two masses, which I can call M1 and M2. And because of the presence of the second mass, there is a force on the first mass, which I will call F. Okay, and this force is the gravitational force, and it depends upon the relative positions of the two masses. In particular, it depends upon the vector connecting R1 and R2 like this. Okay, so with that picture, then we can give a numerical definition of the force. Force is a constant known as Newton's gravitational constant times the product of the two masses divided by the distance between them squared. Okay, so this I'm sure you've all seen before. This is Newton's Newton's law of gravity. Sorry. Okay, so why is this not consistent with special relativity? Well, the most serious problem here is about when you measure F and R. Okay, Newton's law says the force at time t is related to the distance between the two masses at time t. Okay, but obviously F and R1 and R2 are all changing as functions of time because the masses are moving around each other. So to make this formula time explicit, we will put the t's in. So F of t, R1 of t, and R2 of t. And these t's all have to be the same. That means you're measuring the position R1 and the position R2 and the force F all at the same time. Okay. But when we talked about relative simultaneity several weeks ago, I gave you a warning that you must always be careful with the phrase at the same time in special relativity, because in special relativity the meaning of at the same time depends upon which observer is looking. Okay, and here you have exactly the same problem. These t's all have to be the same. That means Newton's law says these things have to be measured at the same time. But that depends upon the observer. Okay, because of the effect of relative simultaneity. Okay, and this is a problem because this means if one observer says that Newton's law of gravity like this is true, then another observer who is traveling with a different velocity, as we've seen before, s and s prime, if s says that this equation is true, then s prime, because he's traveling with a different velocity, will measure the positions at different times because of the relative simultaneity effect, and s prime therefore will not agree whether this equation is true or not. So the problem is exactly the same as we saw with conservation of momentum. Newtonian momentum. If one observer thinks Newtonian momentum is conserved, then a different observer will say it's not conserved. Okay, and Newton's law of gravitation has exactly the same problem. If one observer says it's true, then another observer can say it's false. Okay, so that means it's not a good law in special relativity. So there's another interesting way of seeing that Newton's law of gravity has problems in special relativity, and this is the fact that this force here changes instantaneously if I change the position of the second mass here. So imagine I have an observer on the first mass who is measuring the force of gravity here. If it were possible for me to somehow move this second mass, shake it around, then that would change the direction of the force vector, and this change here would happen instantaneously. As soon as I moved the second mass, the direction of the force would change. But this gives you a way of sending information faster than the speed of light. Okay, in fact, in no time at all, because I could use the shaking of this mass here to encode some kind of signal, some kind of information, like a binary signal, say this is 1 and this is 0. Okay, and this means I could transmit a message from M2 to M1 at instantaneously, much faster than the speed of light. Okay, whereas we've seen in special relativity, when we talked about causality and space-time diagrams, allowing things to go faster than the speed of light causes a lot of trouble. In particular, if you allow things to go faster than the speed of light, you must also allow things to be able to be sent backwards in time. So this would allow messages to be sent backwards in time in special relativity, and that creates a whole load of paradoxes which we usually want to avoid. So that's another sign that something's not right about Newtonian gravity and special relativity. So let me write that too. So Newton's law of gravitation would allow faster than light communication as I said, just by shaking a mass here, I can send a signal faster than the speed of light, and this is something that special relativity says is not okay. Okay, so that's another sign that Newton's law needs to be modified. Okay, so once you accept the fact that Newton's gravity is not consistent with the principles of special relativity, you have to ask, how do we find a new theory of gravity? And this turns out to be a very big problem, and it took Einstein the best part of 10 years to find the solution to this problem. And it requires much greater modification than, for example, the concept of momentum. Okay. If we look at just the concept of momentum, then Newton would define it as a 3-vector p, which is m times dx by dt. Okay, and we saw that when we want to find a relativistic momentum, well, first the 3-vector is replaced by a 4-vector. 3-vector position is replaced by 4-vector position, and time also has to be replaced by this proper time here. But apart from that, the formula stays more or less the same. Okay, so you could say that really this change in the definition of momentum is not such a great change, right? The form is very similar, just 3 vectors now are 4 vectors, and you have to be careful about which unit of time you use in the definition. Okay, but the change required for the theory of gravity is much, much greater than this. You can no longer think about gravity as a force, and you need to think about gravity in a completely new way to come up with a consistent theory. So in the next 2 videos this week, I'm going to describe very briefly and without any mathematics, without much mathematics, what this new theory looks like. Okay.